Good afternoon. Hello and welcome to AEE West's Track 2 Conference, Session 2A, Solving the Problem of Quantifying Efficiency. I'm Steve Cromer. I'm the chair of the CMVP Certification Committee and your moderator today. For those of you, I'm sure all of you are aware of M&V. It's the method of quantifying the impacts of energy efficiency investments. And in a little tip to back earlier today, I watched the keynote session, and it was really interesting what the future of our energy systems are going to be looking like, and the complications that are going to be coming for M&V in the future. So what we've arranged for you now is a great panel of 4 speakers. They're going to walk you through current M&V methods with some tips towards maybe how we're going to be able to address the complex future. Our first speaker is Angel Moreno. Angel Moreno is a certified energy manager with 12 years experience monitoring, evaluating, and optimizing energy systems. She spent years in the field learning how to do real-world conditions impacts on using energy simulation models and equipment operation through site audits and data collection. She's at Frontier Energy, where she provides consulting engineering services for utility demand-side management programs, including program evaluation and custom project M&V. Angel has a master's degree in energy management and a graduate certificate in applied statistics. Here we go.
Great, thank you. Hi everyone, I'm Angel Moreno, a senior program manager at Frontier Energy. We specialize in advanced energy solutions. We have multiple offices across the US. I work out of Austin, Texas. My background in M&V started with doing some calibrated predictive modeling for weatherization projects that have multiple interactive effects. I've also managed a real-time metering project across a university campus, where previously we had been going out in the field to manually collect meter readings. I've also worked on the automation of baseline models creation for commercial energy projects. Most recently with Frontier, I've been leading an impact and cost effectiveness evaluation for a municipal utility here in Texas. Let's get into our discussion now about M&V. We're going on a journey through this labyrinth of measurement and verification. I'm using the metaphor of a labyrinth here because there are a variety of different options for how to estimate savings. And there are various reasons why you may want to employ one method or another. So this labyrinth has all of the normal methods you would generally use to estimate savings, as well as some more advanced M&V options. Unlike many AEE sessions, this won't be a very technical presentation. I'm not going to cover technical how-tos of M&V. I will give you some real-world examples and some results, but for the most part, this is going to be more of a procedural survey, a sort of roadmap to help reset your perspective regarding your options of M&V. And my daughter has been reading these graphic novels called The Olympians that tell Greek mythology stories. One of the stories is about Theseus and the Minotaur. A Minotaur is trapped in a labyrinth and he can't escape because the labyrinth is so intricate and complex that it's impossible to find your way out once you're inside of it. Prince Theseus of Athens decides to go try to defeat the Minotaur. The problem is that even if he succeeds in that, he may perish inside the labyrinth because he won't be able to find his way out. So Ariadne, who is the daughter of King Minos, gives Theseus a spool of thread and tells him to tie one end on the door at the beginning of the labyrinth and trail it along as he goes. And it's kind of a trail of breadcrumbs to help him find his way back. Hopefully, this presentation will be like that spool of thread, a resource to help guide you through your M&V options to help you know when it makes sense to employ one method or another. To start, let's just get familiar with the structure of the labyrinth. The outer circles represent our traditional methods for M&V, TRMs, technical reference manuals in yellow and custom in orange. By TRM, I mean whichever approach you normally take when you want to streamline program rollout. You want cost-effective M&V without a lot of burden of data collection and data gathering. Custom then is whatever you do when those regular methods don't work. It does require usually a lot of collection from the field, site-specific model creation and engineering analysis. Both of these methods have been around for quite some time. You're probably very familiar with the protocols and procedures to estimate savings through either one of these approaches. And I think that there's a lot of confidence around these methods in the industry. And so it's okay if you always stay in this part of the labyrinth and you use TRMs and custom approaches to estimate savings every time. But sometimes we want to evolve. We're looking for something transformational that can help us progress and innovate. And labyrinths offer the promise of that transformation if we can reach the inner circle. Advanced M&V sounds amazing because it's meter-based, it's transparent, it promises to be cost-effective, but it may not always be the best option. And you may face resistance and pushback if you try to change one of your traditional methods to employ more advanced techniques. So your job is to be discerning, to know when it makes sense to head down that M&V path. If you can make it through, hopefully your programs will feel like they've been transformed, you'll feel enlightened, and you can continue to develop more innovative programs using these methods. So let's enter the labyrinth here. When you first enter, you may ask yourself the question of if you have a measure that is eligible to claim savings with the TRM. And if you do, then you'll follow this flow chart to the left, follow the yellow line. And if you can say yes at the next few decision points, then you have a measure or a project that is cost effective. It gives confidence to your stakeholders. They feel good about the savings, that they represent the application, and you're reaching the target markets that you want. You're getting the participation that you're looking for. So you can claim your savings the regular way, and you don't really need to venture further into other M&V approaches. But if you enter the labyrinth and you have a new measure, or it's something that's not quite been vetted yet, it doesn't quite fit the TRM eligibility, you may want to do a custom method, and you would go down a custom path if this was a project you would expect to see one time only. If it's not going to be something that you'll see over and over again, you can just do one-time site-specific custom M&V and custom engineering to get those savings estimates. But if it is something that you expect to see over and over again, maybe you want to build a whole program or portfolio around, or even if it's something that is TRM eligible, but you're not satisfied with it for some reason. Maybe you have some progressive stakeholders who are looking for meter-based savings or otherwise. Then you can continue on and see if there's some other advanced M&V options that might work for you. So the first question that I think you need to ask yourself when you decide to do some more advanced M&V is if you have interval data. It's listed here just as a question. If you have it, really, data handling and data access procedures themselves are their own maze that you have to navigate. But interval data is important for going on to advanced M&V because it enables more accurate predictions. If you are using predictor variables like weather, which is very common, and you're using monthly data, then your predictor variables can only correlate on a monthly basis. But we all know that temperatures change day to day and hour to hour. So interval data can help give you stronger predictor variables. And automation, again, is one of the defining characteristics of advanced M&V. It is one of the reasons that advanced methods promise to be cost effective. It could include automating data collection or automating some portion of your data analysis procedures, because then you don't need to rely on boots on the ground to get the data. You don't have to build a custom model for each project, each time, each event. So it really can reduce your costs over the long run. But automation does require investment, right? The TRMs are so cost effective today because you've already invested in those and you're now at the low point in your cost curve for those. But automation, if you're just getting started with that, is going to require some investment early on. So if you think you're ready to dig into that, then you can continue on. And of course, the data maze, we have to go through this to talk about data management. We're going to talk about how we're going to access and handle our data. The first question being, are we going to use utility meters? And really, whether or not you use utility meters or some other kind of submetering, you still need permission to access that data. This itself can be a hurdle, as anyone who's tried to gather data knows. Just permission itself is one of the big challenges of accessing data. It requires persuasion, it requires security hurdles. So if you can't get data, then you're probably going to have to go out to some sort of TRM method that doesn't require a lot of site-specific data, again, which is okay. But if you do get permission and you're ready to continue on, if you use utility meters, they'll probably have some data standards and regarding the precision and accuracy of those meters. If you're using submeters, then you need to establish that data standard. We need confidence in our data, and so do our stakeholders. And establishing this metering and monitoring standard can help build that confidence in data quality. It can reduce the overall error of your savings estimates as well, if you define the tolerance for error within the meters themselves from the get-go. So a metering standard goes further than what you typically cover in a custom M&B plan. It covers things like the precision and accuracy of the meters, how and where to install the meters, what parameters are you monitoring, under, across what intervals are you going to be logging the data, how are you going to store that data, and for how long. All of these items are critical as we delve into programmatic M&B. As an example, our New York office operates NYSERDA's DER integrated data portal, which is a website that presents hourly performance data for more than 200 DER systems. So our engineers in New York created a data collection and monitoring standard to help ensure consistency in the data that they receive through that program. So once then that you've defined your data metering requirements, then you need to decide if you're ready to automate some portion of that data collection. Again, if you have to send people out every time and gather data manually from the field, or if you're going to borrow utility staff time to provide that data to you, it will add cost to your M&B efforts. If you can't automate data collection, you need to consider some way to streamline it so that you're receiving that data on a regular basis through a method that you can really start to streamline and gain efficiencies in doing that. Otherwise, you're essentially going to be running a custom approach where you're having to invest a lot site by site. So once you have a system for automating or routinely gathering that data, you need to make sure that you make it secure. This isn't really an option, of course, and I'm not a data security expert, so I'm not the one to lead you through that part of the labyrinth, but it is important, it is critical that if you are planning to manage data on a programmatic or portfolio basis, you need to do so safely and securely. And we're not quite ready yet to get to that inner circle of advanced M&B. Regulatory procedures, of course, are in here in the labyrinth with us. These are kind of like hedges that move and appear and disappear at random. When I think about this part of the maze, I think about Alice in Wonderland, who's navigating this nonsensical world that seems to inhibit her more than it helps her. But becoming familiar with the regulatory landscape will help you avoid issues down the line. This really is where you set a strong foundation for your data analysis procedures. And whether or not regulatory approval is required for your project, you still need to follow established and standardized protocols that are recognized by the industry. There may already be some protocols adopted by your jurisdiction, and there is likely some sort of stakeholder body that convenes to discuss issues related to M&V, so engage with them. This is your opportunity to understand their motivations for M&V and allows you the opportunity to have input into those regulations. If you don't already have protocols, then you need to establish them. And I'm not talking about drafting something from scratch. There are many M&B protocols already written. Of course, IPMVP is foundational to MVP or to M&V, and ASHRAE and the national labs also have other protocols for a variety of different modeling applications that might suit your needs. They also have new additions that cover advanced M&V methods. So reference those protocols, adopt them, make sure your stakeholders are on board with how you intend to build out your savings models. So now we're here at the inner circle. We've made it. This is the fun part where we finally get to do some automation of our data analysis. As I mentioned earlier, automation is one of those defining characteristics of advanced M&V. Without it, we're really just doing a custom M&V project because we're creating it from scratch new every time. So let's automate our savings analysis. And first, we have to make sure that we have a good model, which is true of a custom project as well. But when you automate it, it needs to be good repeatedly over and over again across all of the projects that come through your program. We should feel good about our data at this point, that we have good baseline data. We went through the whole data maze, so we should feel comfortable with that. But how do we know then that our model is good? How do we know that our algorithms and simulations are accurately reflecting what's going on in the field? How do we know if they are making reasonable predictions? And fortunately, there are some criteria that can help guide you here. It's not arbitrary. Just a minute ago, we talked about some foundational protocols, and those should include some tests for model fitness. There are a lot of different fitness tests that you can and should look into. You can check how well your predictor variables are. You can check the overall error of your model's estimates, both in the baseline and its predictive capabilities. You can see how well it fits across the intervals. So does it reflect the load shapes that you might see across seasons? And depending on the magnitude of savings you expect, you may be willing to tolerate more or less error. So the model looks good, but can it handle non-routine events? This is a central question of advanced M&V. This right here is that chaos that even if you haven't been fazed by any of the other twists and turns in the labyrinth, data is no problem, regulatory issues are no big deal, this right here may kind of hold you up, because non-routine events are those events that are surprises. They don't exist in your baseline data. Your model doesn't know what to do with them. It can give you some strange results that obviously seem incorrect. Our world right now is filled with these kind of non-routine events that your model may not be ready to incorporate. Because of its nature, this chaos is undefinable. So it's not reasonable to automate all possible non-routine events. But you can still build in some criteria for at least identifying when something seems off. Your automation needs to know enough about the range of normal to be able to know when it's seeing data that isn't normal. And then you can investigate those observations that don't fit. Build time into your processes to investigate these non-routine events and decide how to treat them. And of course, your method should be transparent. We're kind of done with the days of black box modeling where you may wave a magic wand, you do some magic trick, and then ta-da, the savings appear. Stakeholders need confidence in your methods and the results. And to do that, they need to understand what you did. So there are no tricks here, right? We followed all the protocols, we documented everything, and with that, we've made it through this labyrinth. I do want to share a couple of real-world examples. First, let's take a look at a time when automation helped to advance our M&V efforts. We evaluate demand response impacts for large commercial and industrial demand response customers, because these customers tend to have high variability in their load shapes. Simple models don't always work and TRM methods don't apply. In the first year of the evaluation, we tried a variety of different methods to see which had the best fit. And what we learned is that for these customers, having multiple baseline models works best. By testing multiple different models, we were able to use some statistical criteria to determine how well each event fit with each model for each customer. But that was very expensive. You can see on the cost curve here that custom cost line is the top line. We invested a lot, and even if we continued doing that year over year manually, it would still stay very expensive. So we decided to start automating that model selection. So now our automation includes a determination of which method offers the best fit by event, by customer, and it does that for us automatically. So we're able to then spend more time making sure that the data is clean. We now have time to investigate those non-routine events, which do happen. We freed up our time to do that, as well as our client's budget. So on that AM&B cost curve, you can see it's the lower curve there. We did have to invest in that first year. We took what we learned from the costly custom development, but once we automated it, it really dropped that cost over time as we gained efficiencies with it. Now, let's consider a time when advanced M&D wasn't the best option. In Texas, utilities can claim savings for heat pumps using a deemed value from the TRM. Equipment eligibility covers, traditional heat pumps and mini split heat pumps, and they apply to single or multifamily. This makes it really easy for utilities to expand the reach of their HVAC programs. And if you want to claim savings for this project, they could have gotten about 1,400 kilowatt hours of savings. Of course, climate and system specs can change that number, but to claim these savings, really all you need is proof of install and an equipment spec sheet. Now, the cost curve for this, at this point, was very low because we had already invested a lot in the TRM development. We spent a lot of time in the early years building out those savings so that they would be an accurate reflection of what we would expect those projects to receive. So the cost for that was very low, but we did have a stakeholder at that time who felt like the TRM didn't reflect the savings potential of mini split heat pumps. So we created a control and test group to monitor both traditional and mini split heat pumps in a multifamily building. We collected data manually using system level submeters. And we used just the simple difference between the two groups to come up with the savings. And we got about the same savings as we would have using the TRM. So we never ventured down an advanced automated M&V meter-based savings for this program. It would have required solving some of those considerations that we discussed in the labyrinth. Would we keep using submeters? In a multifamily program, that would be a challenge because we'd need permission to access those meters every time from multiple different occupants, or we could switch to using utility AMI meters and build a whole building level for it. But we really didn't see any potential for additional savings, so it just wasn't necessary to do that. Here now is a quick guide summary of our journey. We learned that transparency is important, regardless of which M&D method you apply. Be sure to document your work and be ready to share it with stakeholders. And if you don't have access to site-specific data, you'll probably have to use a TRM. And if everyone is happy with that, then go for it. If you can't automate your data access, or you have a technology that is kind of a one-time deal that you don't expect to be very popular, you can M&D it with custom procedures. However, when you are ready to integrate M&V into your portfolio on a programmatic basis, and you have the ability to automate your data processes, then you might be ready for some advanced M&V. Model validity and a procedure for determining non-routine events are critical here, and don't forget to make sure that your foundational protocols are approved by your stakeholders. And that is it for me, so thank you all very much for your time.
And thank you, Angel. that was a great introduction to our panel and a walk through the basics of M&V up to the current advanced methods. A couple questions for you. You talk about automating the
Sure.
process of developing a model. What tools did you use to automate the model selection process for your commercial and industrial demand response program?
Sure. We used R to automate that model selection process. R is an open source programming language. It enables rigorous statistical analysis, and you can script in R to process energy analysis. It readily calculates a lot of the model fitness tests that we use in the industry, so we thought it would be a suitable option. When we automated it, we looked at RMSE, bias, and standard deviation, and so we did a piecewise model to go ahead and automate that selection. You can use Excel to automate some of this if you're doing some simple automation, but for this particular project, it was too complex of an endeavor that it really wouldn't have been efficient to model that using Excel or to automate it in that way.
Great, and like any science worth its weight, we have all our own language, and you say R as your tool, as a software tool, but you also have R squared and other things that we talk about. So the labyrinth has other paths to navigate. Can you tell us more about, you've got a model, how do you, what quantitative methods do you use to test R squared, RMSE, CVRMSE, another whole set of language around how good is the model?
Sure, right, model fitness tests, there are lots of options out there for determining the accuracy and being able to measure the uncertainty associated with the estimates that you're getting from it. R squared, of course, this is a measure of how much variation in your consumption can be explained by the predictor variables that you used in the model. So R squared is useful in that sense. However, it does have some issues, especially when you get into running multivariate regression. You'll find that as you add more variables to explain the change in energy, that your R squared will improve, and so it'll start to look like you're getting a better fit of your model. However, that increase does not take into account whether those predictors are statistically significant, by which I mean, is the change due to those additional variables, or is it due to random chance? And increasing the R squared doesn't necessarily consider that. RMSE, which is the root mean squared error, it's, on the other hand, it's an overall measure of how far off your model estimates are from actual data. So, as far as which types of tests are better, I would say you should use a few of them because they'll just give you a better overall picture of your model accuracy.
Great, and so advanced M&V, as you said, is here. There's still a lot to be worked out in actually perfecting it and applying it and automating it, so to speak. How do you think it's going to, how do you think it'll ever replace TRMs and deem savings methods? And will it replace CMVPs? Will it replace the need for educated, smart people on the ground to actually go look at facilities?
Well, gosh, I hope not. I hope we don't all lose our jobs from this. I do not think that it will ever entirely take the place of that. Especially when you're automating, you still need someone who has that field experience to be able to understand when you're seeing something that is not typical. The model won't be able to identify anything unless you tell it to do so. And so that's where our expertise comes in. I also think that there are some smaller savings measures that can really be impactful in aggregate in a portfolio, but using a whole building AMI type meter, you may not be able to isolate those impacts. There's going to be too many other loads that are confounding what you're seeing. And so it really won't be cost effective because of their small impact potential to submeter them in that way. You are seeing some more smart appliances and end use plug loads that are Wi-Fi connected and Wi-Fi enabled. You may be able to pull data off of those, especially with EV charging equipment. You can trend the power draws through there. So that may be an option to access those, but I still think you always will need someone who has the experience, understands the equipment that we're trying to measure. So yeah, it's going to go hand in hand.
And regarding TRMs, what do you think about replacing TRMs?
I think TRMs will always be useful because you always need a cost-effective way to roll out programs. You may find that the algorithms and deemed values that are in there may change slightly to incorporate some more meter-based values, but I think they'll still continue to kind of
Great.
inform evaluation.
Well, thanks, Angel. I think that's all the time we have, and I appreciate your talk. And we definitely need to talk more later. I agreed with everything you had to say and look forward to learning more about how you're applying advanced M&V in your Texas programs and at Frontier in general. So thank you very much.
Great. Thank you. Appreciate it.
Yeah, sure. All right. Our next speaker, number 204, is Mike Christensen. Mike Christensen is the Director of Customer Engagement at Energy 350. He oversees 350's customer engagement efforts, including outreach, marketing, strategic energy management, delivery, and external business development. Mike has over 15 years of experience in the areas of energy efficiency, environmental policy, and research and development in both the public and private sectors. Mike received his Bachelor's of Science and the Master's of Science degrees in Mechanical Engineering, OME, cum laude from the University of Michigan. And Mike enjoys in his spare time snowboarding, cycling, brewing beer, and spending time outdoors in the Great Northwest. So Mike, take it away.
Okay, well, thanks everyone for joining me today from the comfort of your bathrobe. I'm here to talk to you today about the wonderful world of M&V, added expense or cheapest energy savings available. The thesis of this is, that M&V is somewhat an overlooked last step in an energy efficiency project, and sometimes treated as a little bit of a check the box exercise, right? I'd like to make the argument today that when applied appropriately, M&V can be used to eke out some additional energy savings, which makes it some of the cheapest sources of additional energy savings available to a utility program. So without further ado, I'm just going to jump in here and start out with just first a little bit of background about Energy 350. So we're a roughly 40-person and growing energy efficiency consulting firm based in Portland, Oregon. And we're pretty nerdy and proud of it. We're mostly engineers, the majority of which are PEs, also some CEMs and CMVPs tossed in there for good measure. And we specialize in energy efficiency program delivery, energy studies, both on the commercial and industrial side, building tuning and retro commissioning, strategic energy management, research and evaluation, also some field demonstration of advanced technology in there, and then some energy efficiency policy and code related work. Our mission statement on our website is that we mine energy efficiency as a resource to displace power plants, save businesses money, and protect the environment. So in short, we love this stuff and love to nerd out on it. I'm glad to be able to do that with you today. I will be getting into the weeds just a little bit here on some data. So for those of you who are as nerdy as we are, get out your slide rule and pocket protector. And for the rest of you, I'll try my best not to completely put you to sleep today. So next slide. First, let's start out with defining the problem. Why should we care about M&V, right? I'd say that for most of the custom large commercial industrial energy projects that we work on these days tend to be largely dependent on controls, right? It's not necessarily the nameplate efficiency alone that drives energy consumption. It's how the equipment is operated that truly matters in the real world. And aside from new construction, energy efficiency projects are almost never third-party commissioned. This is a very important thing to note because the energy study that's done up front often assumes some very efficient operation of the new equipment that's going in. In these big custom projects, you're just unlikely to get those savings estimated in the study without some due diligence on the back end to verify it. Also, the controls of these systems are usually set up by field techs. And nothing against field techs, but they'll often program the controls for reliability, not for energy efficiency. And who can blame them, right? Not only have they not read the energy study or seen the recommendations that we've drafted on how to sequence and commission the system, but honestly, they might not even know that they're working on an energy efficiency project. They're just putting in some new stuff, right? Which is to say, they're basically just doing their job. And then the last point here is that we often find that when the customer and the contractor consider the project to be done, it's probably not producing all of the energy savings that it could be, right? There is definitely a role there for us to play to squeeze out some of those energy savings for the utility program, and we take pride in doing so. Okay, let's go to the next slide here. So the evolving role of M&V. What I'll call old school M&V was traditionally used by programs or part of a performance contract to true up savings on the back end. Now, that's fine, but the downside of this approach is that since these projects are rarely commissioned, as I just pointed out on the previous slide, energy savings often fall short, right? So we come on the scene, do some M&V and say, well, we estimated in the study that you would save X, and verification shows that you saved 0.8X. We'll just pay you for that. Well, that's not good enough. You know, we'd like to make the argument that, you know, hey, where's the rest of that 20%? Let's go out and get that. That is an additional step that a lot of programs just don't do, either because they're not that technical, or they simply lack the resources to dig deep enough. So we really see this as an opportunity to harvest savings that would otherwise be left on the table. So with only minor incremental effort and an approach that combines commissioning with M&V, we can effectively use the M&V results to inform the optimization of the system and thereby maximize energy savings for the program. This isn't just a one and done thing, but more of an iterative approach. And I'll get into some examples shortly here that kind of illustrate that. So our results. Over the years, we have squeezed anywhere from 10% more energy savings to twice the energy savings out of projects through these enhanced M&V efforts, I'll call them. It really just depends on the project and the situation. Last, but probably most importantly, we spend as implementers a lot of time and client money doing what we do. So let's say we spend an extra $3,000 on some enhanced M&V and save an additional 20%. Well, those savings are being harvested at a fraction of the cost of the project overall, right? So one can argue that this is the biggest bang for the buck in the program, and going out and getting that last 20% is really key. So let's get into some real world data here to illustrate my point. So this is a chiller project where we just weren't really happy with how the equipment was initially set up upon install. So we had to work with the field technician and challenge his assumptions a little bit. So the project was studied and analyzed based on the manufacturer's stated minimum refrigerant differential pressure, DP, right? When we got there for M&V, they were following our recommendation to control based on DP, which is great, but the technician had set a much higher and therefore more conservative DP set point than what the manufacturer had indicated was possible. And that was used in the energy study. So we started to challenge the tech a little bit on that. We said, you know, what is Trane's stated minimum? He said he wasn't sure, but you know, whatever he had set it up at, 6 or 8 PSI, was the lowest he was comfortable going. We said, well, you know, this chiller just isn't performing per Trane's rating, so you guys need to talk to each other. He called the factory and said, okay, the factory says we can get as low as, I don't know what it was, 1.5 or 2 PSI, but I'm just not comfortable with that, he said. So like, now what do you do, right? As the energy engineer, the guy is uncomfortable pushing it down to what his own company's ratings say he can. So now is where the negotiation begins. And I think on this project in the end, we met somewhere in the middle, maybe, you know, 2 or 3 PSI, but the point is we were able to squeeze an additional 10% or so of energy savings, which is the difference between the orange and the blue trend lines here on the chart, for a minimal amount of effort. Sometimes it takes several rounds of iteration to do it and a lot of back and forth negotiation to get this stuff right. But you know, it probably took us 6 weeks to finish this M&V, where otherwise it would have taken 2. But in terms of man hours, it was practically nothing. It's just a set point, right? So it's well worth the effort to dig a little deeper. Next slide. So here's a much smaller project, but still illustrates the point. So this is some heat pump data for our office, Energy 350's office building, or the office building we share with others. And during the build out of this office, they installed some really nice high efficiency heat pumps. But because the units were programmed to be in what's called comfort mode, which aggressively kind of tries to keep the space within 1 degree of set point all the time, these heat pumps were often running backup heat, which is an electric resistance coil, right? Effectively wiping out your efficiency. And so there's two figures here. The figure on the left shows the baseline, as observed, and the one on the right is after we commissioned it, or retro-commissioned it in this case. The gray line is the backup heat power, and the yellow is the compressor and fan power, the heat pump side of things. So let's see if I can get the animation here. So yeah, as you can see in the dotted red line there, in the morning when the occupied hours begin, the backup heat comes on right away and stays on because it's trying to maintain 1 degree of set point as quickly as possible, which is just not realistic or necessary really. So just by relaxing that requirement, we eliminated most of the backup heat from coming on, as you can see on the right, and then now the heat pump is doing the work that it was supposed to do. Lastly, we being the tenants never really noticed the difference in terms of comfort. So all around a good thing. This next one is an example of stuff just sometimes slips through the cracks due to a lack of proper M&V. In this case, due to poor coordination of trades. So here we're showing a large air handler, originally built with inlet guide vanes to control supply fan airflow. At some point in the past, before we got involved in the project, they retrofitted this air handler with a supply fan VFD. So we were out there doing an energy study, walking through the building, and at first glance, your instinct as an energy engineer is to think, oh, I see this unit already has a VFD, move on to the next thing, right? No opportunity here. Well, we opened up the door to take a look inside, and sure enough, as you can see in that middle picture, these are inlet guide vanes, right? An inefficient way of control. And not only were these guide vanes still intact, but they were actively controlling the supply fan. And what you cannot see in this crappy picture on the right is the VFD speed. It's pegged at 57%, so all the work is still being done by the inlet guide vanes, even though this has a VFD. So what the heck is going on here? How does this kind of thing happen? Well, like I said, this project involved different skilled trades who sometimes don't talk to one another. And we actually see this a lot more than you'd think, especially in fan and pump projects. The electrician installs the VFD, but it's not his job to mess around with those inlet guide vane things, right? That's a mechanical job. It's someone else's job to do. As a result, sometimes these details just slip through the cracks because no one person is responsible for the installation of this project as a turnkey thing. So this next one, there's a lot going on here. It's pretty nerdy, but bear with me and I'll break it down because it's a really cool example. Here's some trend data from a new chilled water plant. On the primary y-axis on the left, we've got power, so chiller kW, cooling tower kW, and overall plant kW. The secondary y-axis on the right is temperature, and we've plotted dry bulb outside air, wet bulb outside air, and condenser water temperature, both programmed, the program set point and the actual condenser water temperature. So the general school of thought for chilled water plants is that you should drive down your condenser water temperature as low as possible to save energy at the chiller. It may cost you a little cooling tower fan energy, but the chiller is such a big user of energy that it's worth it. And while that's true to an extent, every system's different and the devil is in the details. So we need data to drive our decisions. So as you can see in this mess of spaghetti noodles on the screen, the green line is the condenser water temperature set point. It was initially set somewhere around 60 degrees. So the customers thought, well, it's nice and low, we're nailing it, no opportunity. But in reality, that condenser water temp set point was set to a temperature that the cooling tower fans just weren't able to achieve. So you can see the actual condenser water temp trend line in black. It's, in this case, it kind of hovers between 74 and 76. It never drops below that. And as we see in the gray line on the very bottom, those are the cooling tower fans, and they're pegged at 100% speed. They're trying to keep up, to keep that, drive that condenser water temperature as low as the set point was calling for. So we have an opportunity here. We had them program a floating wet bulb approach strategy, and which is where you let the condenser water temp follow wet bulb at an offset or an approach. And what you can see here is that we implemented the controls change here to in the green line to let that float with wet bulb, and you can see that it begins to track it at an offset, track that blue line. It takes some time for the system to respond, but what this does is raise the condenser water temperature set point slightly, shifting a little bit of work back over to the chiller in orange. But that increase is more than offset by the dramatic reduction in fan kW in gray at the cooling tower, and that's because of the affinity laws, right? So it's a worthwhile trade-off. In summary, this set point was simply unrealistic. By letting the M&V data be our guide here, we were able to slow down the fans, take advantage of the affinity laws, and optimize the overall plant kW following our M&V effort. This one is actually pretty similar to the last example. It's a refrigeration system where the approach temperature, again, was just set unrealistically low. The light blue line on the bottom is the outdoor ambient wet bulb. The dark blue line above it is what the control system is calculating the condensing temperature should be based on the approach temp that was programmed, right? But as you can see in red, that actual condensing temperature of the system just isn't able to meet set point most of the time because the condenser's undersized. Meanwhile, the fans are at 100% speed, as you see here in green, staying at full speed most of the time except at night, where it's actually able to meet the set point and the fan speed will drop. So it indicates a programming adjustment is needed. This graph only shows the pre, not the post, but you get my point. Okay, this one's fun. This is an M&V site visit for a project that replaced a bunch of steam traps that were failed at an industrial facility. So I'll play this video here. So we were called out to verify this project, and we noticed some weird stuff going on. You can see there's this geyser spouting from the roof of the building. And we're like, wait, what the heck is that? What's going on? What that is condensate being blasted out of the deaerator tank relief pipe, which is designed to allow a small amount of steam to escape before it's returned to the boiler. And either the wrong trap was installed or it was installed improperly, such that it failed open and a massive amount of steam was leaking by the trap, blowing it out of the DA tank. And keep in mind, this is after the contractor and the customer said, yep, we're all done, come take a look out so we can close this and get our incentive check. In this case, this is an energy conservation project that likely had increased energy consumption relative to the baseline before we noticed this problem during M&V. In the interest of time, I'm going to skip this one. It's another cooling tower fan programming project at smaller scale, but I'll move on here. Another fun video to close with. Question or assume nothing, question everything, right? This is one of my all-time favorites. So this is a project at a high-tech site where we didn't get involved with the facility until they had just replaced their relatively new chillers. They were a couple years old, and the customer decided to replace them because they simply weren't getting the performance out of them that they had expected, and it was affecting production. So this is, not much less than a $1 million project to replace what they thought were inefficiently operating chillers, right? Well, you can see here in the video, during the install process, they cut into the chiller piping and found this little Easter egg here that had been sitting in the pipes for several years, right? Presumably from the last chiller replacement. So that angle grinder, whatever that is the source of inefficiency. They didn't need to spend $1 million on new equipment, right? Kind of makes you sick, doesn't it? Oh, poor guy probably lost his job. All right, anyway, I'll wrap up here. In conclusion, you know, it's less a function of the nameplate rating. It's how equipment is controlled in real life that really determines energy savings. An analogy that I often use is it's like the customer paid for a Ferrari, but doesn't know that the parking brake is stuck on. And enhanced M&V can really help take off that parking brake and make it operate the way it's supposed to. As we said previously, contractors and field techs often end up being the key decision makers on these projects. And most of the time, energy efficiency isn't considered, even if it's an energy project. So without bringing in an expert to do proper M&V, utility efficiency programs are at risk of leaving some of these savings on the table, or they risk poor valuation down the road. Either case, you end up getting bit. And finally, from a program implementation perspective, the incremental savings gained through a combined commissioning and M&V effort can be harvested for really just a fraction of the cost of the overall project. This makes M&V some of the most cost-effective savings available for the program and for most projects. And with that, I'd like to thank you for staying awake, and I'll take any questions you might have at this time. Also, here's my contact info. Feel free to reach out to me offline if that's easier for you, and I'd be happy to have a conversation with you.
Well, thank you, Mike.
Okay, well, thanks everyone for joining me.
Great presentation. Angel earlier in the first section walked us through the labyrinth a little bit, and you've just walked us, I think, down into the weeds a little bit. And I like a lot about the overlapping of the interval meter and the advanced metering, and then the details of what you can start to see in the operations over time. And I'll just say that historically, it's been a promise of M&V that by doing it, by building the feedback loop, you could find and harvest out more savings. So it's always one of the benefits that we've always talked about. So thanks for that. In terms of bringing it back, and again, I'll just say as well, it's good to work with you guys and your colleagues at Energy 350 on evaluations out here in California as well.
Thank you.
So
appreciate it.
Yeah, sure. And so you talk about the specific methods, but are you applying any one of the IPMVP protocols specifically, or any one of the options in the IPMVP that you guys find is better or worse than the others, or how do you approach that, to selecting which option you're going to use?
Yeah, it really just depends on the project, the scope, the magnitude of savings, whether it's new construction or retrofit. I'd say, typically for folks that might remember, there's 4 options. The first 2 are retrofit isolation. The second 2 are whole facility modeling. And for the project examples that I walked you through during the presentation, those were all retrofit isolation. So drawing a control volume around just the system or areas that the baseline and energy efficiency measures need to be analyzed around, and doing detailed data logging and analysis of that data. So we have a very vast array of tools at our disposal, from real power meters to ultrasonic flow meters, et cetera. And so for large custom retrofit projects, that's really our go-to. Now, I'm also a big fan of option C, the statistical models that Angel was talking about. We do a lot of retrocommissioning activities that's looking at an entire building. We also deliver strategic energy management, which is implementing a wide variety of measures across a site, where doing retrofit isolation would be very difficult, right? So it's more cost effective, and it's not going to let the savings slip through the cracks if you're able to harvest those in a whole building model.
Great. Well, building on that just a little bit, and I've been hearing the word, even at the EVO documents that are coming out, meter-based M&V, and it seems to me that both option B and C are meter-based, right? Do you have an interpretation for the word meter-based M&V?
Yeah, it's a good question. Whether it's AMI or doing field deployment, sub-metering, it's still taking measurements, right? It's not just using equipment specifications and a couple of assumptions like you might do for option A. So yes, absolutely. I think in our view, meter-based M&V is a critical component of a good verification plan.
And can be either option B or C. Okay, great. I think that's something for the industry to keep our vocabulary and our meanings as tight as possible, so we don't confuse people in this labyrinth that we're all entered. Now we're into the labyrinth. How do we get stay here and stay happy? Great. So how do you ensure once you do your projects you're getting the efficiency you want? So we saw some of your field work, but it sounds like people that are specifying the stuff up front it's not good enough just to specify it up front. So what do you recommend to people to sort of avoid these problems of the 80% or the partial savings problem?
That's a good question. I think first of all, doing a good detailed energy study, you know, ASHRAE level 2 audit or equivalent, that's actually going to have some baseline measurements incorporated to it, some meter-based baseline measurements. So typically what we'll do for a custom capital project is a minimum of 2 weeks of real power data. It doesn't have to be anything that's working in live equipment. We can work with facility engineers to install loggers on de-energized equipment, make sure we're safe. But anyway, 2 weeks of meter data, followed by a careful analysis. Usually takes the form of an 8760 model, an hourly model that may take into consideration external factors like weather or occupancy to estimate the baseline consumption. And then using those specs, we can do a proposed, a new baseline with the energy efficiency measures implemented. And that's an estimate, right? That estimate is good enough to make an incentive offer to proceed with a study, but we're not just gonna take that number and call it done. M&V is a big part of the overall energy project. So based on those estimates that we've looked at up front and a list of assumptions, we need to do some post-installation M&V, typically, or I guess I'd say ideally, mirroring the same type of measurement that was done up front, so that we're looking at more of an apples-to-apples comparison, making any adjustments we need to, and yeah, taking it from there. But I think that the key takeaway there is that initial upfront study should have a very detailed M&V plan proposed in it that the M&V engineer can actually follow to make sure those savings are realized.
Oh, that's certainly what we teach in the IPMVP class, is that the core and the soul of IPMVP is the plan, documenting what the assumptions are and then being able to follow that. And then it takes a professional to write the plan, but maybe a technician to follow it. All right, so you mixed up a couple things in terms of you brought together a couple of concepts that I believe are still confounding people in the industry of just energy efficiency. Angel did it as well. We're talking about program evaluation, and at the same time we're talking about projects. And I'm wondering about, again, the detail you get into, knowing that this is costly stuff. So a custom project, maybe you can afford a little bit more because it's going to be leveraged across the whole portfolio, versus a performance contract where every site has to pay for its own M&V. So can you talk about like what kind of costs can a custom project absorb when it's one-off versus maybe a utility program? How do you get the utilities to pay for these more advanced M&V? More thorough M&V activities, I guess. That's a lot of questions all in one.
Yeah, well, I mean, in our experience, we're an implementer, right? So we work on industrial program delivery. Our main client is Energy Trust of Oregon, and under that program, we have the latitude to spend a little bit of extra time on the back end to do M&V. The initial study up front is a fixed price study. Usually either done in-house by us or by a third party, depends on the project. So within the scope of that work, the M&V plan is developed and defined ahead of time. It's up to us to then on the back end make sure those savings are realized. And depending on the size of the project, as we said earlier, it might not warrant a ton of enhanced M&V, but what we typically find is that, let's say it takes an energy engineer an additional 20 hours to do enhanced M&V. I mean, if we're talking a couple 100,000 kilowatt hours of savings project and we can squeeze out 10 or 20%, that's pretty cheap amount of implementation overhead for those kilowatt hour savings. So that's a long way of saying we have a little bit of wiggle room on how we do it, but that's the way we go about it.
Great. Again, you're defending the value of M&V by saying you're going to be able to squeeze more savings out if you do it right, if you follow through a little bit.
Right.
All right. So back to, again, and one of the worlds we always have to talk about with EVO and IPMVP is how do we link to other organizations? And of course, we always just throw out the word ASHRAE. So when you say, all right, ASHRAE level 2 or maybe even level 3, are you recommending one of those over the other? And how do you fit ASHRAE into your whole program?
I'm not recommending one or the other, but just to be clear, most of the custom capital projects we undertake are an ASHRAE level 2 equivalent.
Great. Well, I think that's about it. Mike, thank you very much. And again, look forward to working with you and your colleagues at Energy 350 in the coming year.
Thanks, Steve.
Thanks. Yeah. All right. Well, our next speaker is going to be Mr. Peter Grant. And Mr. Peter Grant is deep in the hot water here. And I'm sure you've gotten that joke many times, Peter. Peter has worked in hot water research. And I believe that means the hot water that's usable for showers and whatnot inside buildings, not just geothermal. Since 2007 at institutions including the National Renewable Energy Laboratory, NREL, LBNL, Lawrence Berkeley National Laboratory, and the European Academy. His projects at those institutions have included laboratory testing and simulation model-based research, primarily creating experimentally validated simulation models of hot water systems. He's also served as a technical expert advising the regular Title 24 update process. That's the California building code process where they have energy codes as part of the building codes. And so they use a lot of simulation models to verify what level we want to put into our new code. Peter is an annual presenter at the ACEE Hot Water Forum and at any event where people are interested in his area of research. So Peter, take it away.
All right. Hello, everybody, and thanks for coming to this presentation. In this presentation, I'm going to describe a concept that I've come up with to you, a concept that I call model-enhanced monitoring. And it's really based on this one question of, can simulation models improve measurement and verification? I also want to be really clear, this is not a presentation where I'm telling you about something that I've done that has worked fantastically and everybody should adopt instantly. It's definitely not that. It's a presentation where I'm telling you, I have this idea, and this idea might work, and I think we should discuss it, and I think we should consider it, and I do have a project coming up where I'm going to try it. But, we should definitely have this conversation, keeping that in mind. So here's a quick outline of what I'm going to tell you about today. I'm going to describe the problem statement, this issue that I'm trying to solve with model-enhanced monitoring. And then I'll talk a bit about the strengths and weaknesses of models. And I'm sure everybody in this presentation knows about the strengths and weaknesses of models. So it's not, educating you on them. It's really just trying to bring these thoughts to the top of our mind because they're relevant to the discussion. And then I'll dig into the proposed solution. I'll dig into how I think simulation models can help improve measurement and verification processes and how we would go about doing that. And then finally, I'll talk about an example. It's based on a project that we have coming up where I expect to start doing this next year. And I hope that, walking through how I intend to approach that project can help really solidify some of the concepts so that you know exactly what it is I'm proposing. And then we'll get into probably the most interesting portion of this, where we will have the discussion. And I really want to hear what you think about this process, whether or not it will work, how you might recommend improving it, or other areas where we could consider trying it. So here's the problem that I'm trying to solve. And that's really, in measurement and verification, as I'm sure everybody knows, we're kind of comparing apples and oranges, right? We have a base case system, and we have a retrofit case system, and we monitor the base case system, and then we put in the retrofit system, and then we monitor the retrofit system. And we use the data from the base case and the retrofit case to compare the performance of the two and say how the retrofit case worked. But we're not really comparing the same situations, right? These different measurements happened on different days. There was different weather on those different days. The occupants in the building behaved in different ways. There are other changes that I haven't thought of or included here, right? And all of these changes will impact the performance of the system. So we're really comparing the performance of two different systems with two different scenarios. And, we're really not comparing the same thing. We've got our base case, which is kind of like an apple, and our orange case, or our retrofit case, which is kind of like an orange. And this can be a big deal. For instance, I work in water heating, and water heating use patterns, or hot water use patterns, what's called a draw profile, can vary significantly from day to day. Some days I wake up in the morning, take a shower first thing, and then go to work. Other days I go to work and then I go for a run afterwards and I take a shower. Some days I take showers both times, and there are days I run the dishwasher, days I don't. And so you end up with very different use patterns every single day, which is definitely going to impact your base case to retrofit case analysis. And at least in these research water heating projects, the field monitoring projects, the traditional solution is to really kind of average it out. This means that you have to install the retrofit case in many different sites, and you have to do it over a really long monitoring period. And this way you basically get so many days that even though no two of them are the same, you can kind of do a pretty good job of figuring out what happened. And then you can also invest time to kind of normalize the data for different weather patterns or different inlet water temperatures, etc. And it works. It does work. It gets usable results. But the problem is it takes a lot of engineer time. More sites means more engineer time. It means more data, which means more engineer time. It means more analysis, more making sure the systems work, which means more analysis, or which means more engineer time. And as we all know, engineers are expensive. So a lot of engineer time costs your client basically a gigantic pile of money. And I'm arguing, well, no, I'm not arguing, I'm theorizing that we could get potentially better results while not costing our clients nearly as big of a pile of money. So we could deliver better results at lower cost and really get competitive advantage and deliver better value to our clients that way. So moving on from the problem statement to talk a little bit more about what I'm proposing, the first step, of course, is to talk about the strengths and weaknesses of simulation models. And there are certainly different quality of models out there, but I think the majority of models are a very accurate representation of the physics and the control logic in different pieces of equipment. These are the models coming out of our national labs. They're models coming out of consultancies like Ecotop. And they're very, very good models. They can predict what the behavior does if they are given the correct input information. Of course, the weakness with simulation models is that you pretty much never have that correct input information. You have to assume what the weather is going to do. You have to assume how the occupants are going to behave. And it's impossible to get that right. We can get it pretty close, but it will never be precisely what happened because it's an assumption. And so the end result is that typically our simulation models don't give us the right answer. They give us a somewhat reasonable guess. And that's valuable, but that doesn't really solve this measurement and verification problem. Unless you have monitored data, which in a measurement and verification project you do. You monitor the base case, you monitor the retrofit case, which means you no longer need to make assumptions about the weather patterns. You no longer need to make assumptions about the occupant behavior. You have your monitored data, and suddenly your monitored data becomes the inputs to the simulation model. So now you're combining the accurate physics and control logic of the simulation model with the accurate weather and occupant behavior data that you monitored. And so this leads to my proposed solution of model-enhanced monitoring. We use the monitored data as inputs to the simulation model. And because of that, we can get very accurate model results. So you create two different simulation models, one for the base case and one for the retrofit case. And then you input the monitored weather and occupant behavior data into both models for the entire period. And in this way, you now have the results from the base case simulation model saying what the base case would have done on every day during the monitoring period. And you have the results from the retrofit case model saying what the retrofit case would have done for every day over the monitoring period, which means you have two sets of results with the same input data, showing how these two systems would behave in the same cases. Now we're comparing apples to apples. Okay, and so to try to make this concept a little clearer so you can really understand what I'm proposing doing, I'll walk you through an example of a project. And this is a project that we've just started. You know, we're just getting going on monitoring, and so I'll be experimenting with these techniques probably next summer when we have all of the data. And this project is a PG&E funded codes and standards project located in Davis, California, where we have 10 heat pump water heaters installed in the field, and we're going to be implementing load shifting controls. And our goal in this project is to really understand what are the impacts of load shifting controls? Do we get the benefits we're hoping for? Are there other problems we need to overcome before this goes mainstream? Now, for those who don't know about load shifting with heat pump water heaters, don't worry, that's what these next two slides are talking about. And so this is really showing the control strategy that's used when load shifting with heat pump water heaters. To give kind of a big picture overview, you know, the utilities, at least in California, have kind of competing problems with balancing the grid at different times of day. I'm sure many of you have heard of the duck curve, and that's what we're looking at, where there's one problem of we have so much solar electricity on the grid that sometimes we need to mitigate electricity to avoid problems of overgeneration around midday. So the utilities really want people to consume electricity at midday. And then so only a few hours later, there's less solar power, everybody's getting home from work and turning on their air conditioners, and there's so much demand that the utilities have trouble meeting the demand just a few hours later. So and that's from the utility point of view. There's also time of use rates now, so people can save money by consuming electricity at noon instead of in the evening. And since there's more solar power on the grid around noon, you can really reduce your carbon emissions by consuming electricity at noon to provide services that you use in the evening. And so this plot really shows how we're trying to change the control of a heat pump water heater to take advantage of that. Now, keep in mind, water heaters are very reactive devices, especially storage type water heaters, where you've got a big storage tank of hot water. The device keeps it at the set temperature. You consume hot water, the water gets colder, it heats the water back up to the set temperature. That's all it does. And a little more background information for those who don't know, heat pump water heaters have two different heating elements. One is a heat pump, which is low capacity, heats the water slowly, but is extremely efficient. And the other is an electric resistance element, which is high capacity, heats the water quickly, but is very inefficient. And so they usually try to use the heat pump as much as possible and then engage the resistance element kind of as a last resort to make sure people get the hot water, even when they use more than the heat pump can provide. That's going to come into play later in the presentation, just a bit of background information. But for now, what we're really showing is the control strategy that we're using in load shifting. And the blue data represents the base case, where we have a set temperature of 120 degrees, and it's constant throughout the day, and the water heater only does what it needs to do to keep the water at 120 degrees. Then in the load shifting case, at 10 a.m., we increase the set temperature from 120 to 135 degrees. And keep in mind, this is an example control strategy. We are experimenting with different set temperatures and different timings. So this is just to show the concept. But so yeah, if we increase it to 135 at 10 a.m., and then we keep it there until 4 p.m., where we reduce it back down to 120. And at 10 a.m., when we increase the set temperature, the heat pump engages, gradually heats the water up to 135. In this example, it gets there around 3 in the afternoon, and then it holds it to 135 until 4 p.m., wherein at 4 p.m., we reduce the set temperature back down to 120, and the temperature gradually decreases as heat's lost to the ambient surroundings, and as people use hot water and withdraw energy from the tank. And so this next slide shows why we're doing that. This second plot down on the bottom shows the amount of energy that can be withdrawn before the water heater has to heat water, assuming a set temperature of 120, right? So from 10 a.m. to 3 p.m., you see the amount of energy that can be withdrawn before having to heat the water gradually increases until it's roughly double the amount as in the base case situation. And then it holds steady until 4 p.m. as we maintain that 135 temperature. Okay, so let's run through what this might look like on a given day in terms of the model enhanced monitoring. And so this slide shows, what might happen in the base case, where the red data shows occupant hot water consumption, and then the blue data shows electricity consumption, and it's monitored data in the base case. And keep in mind, when I say monitored data, it's an example of what monitored data might look like. This is an example I created for the presentation. We're not far enough in the project to actually provide data yet. But what we see is that in the morning, there are 3 separate showers. 3 people take showers back to back. And halfway through the second shower, you can see the electricity consumption increases a little bit and holds steady. And that's the heat pump engaging, trying to heat the water and make sure the occupants get enough water. But then, there's not enough storage. The heat pump doesn't have enough capacity. And halfway through the third shower, the electric resistance element has to engage to make sure the occupants can get hot water. And actually, it's possible, not likely, but possible that the third shower got cut short for cold water reasons. And so then it keeps using the electric resistance element to get the water in the tank back up to the set temperature so it's ready for the next person. And then we can see about the same thing in the evening. We've got 2 people who go for a run after work and they take showers and then they all eat dinner and then they run the dishwasher. And again, halfway through, it engages the heat pump to try to keep the water hot, but it's not enough. And so by the end, it's using the electric resistance element to make sure everybody's getting the hot water that they need. And so let's assume we've got that data for the base case. But what would happen if we implemented load shifting on that day? From a monitoring point of view, we'll never know. We can implement load shifting on any number of days, and they'll never be exactly that day. Maybe we'll get some pretty close, but never exactly that. So if we want to know how load shifting would perform on that day, we can simulate it. We can put the monitored data into the simulation model of the case with load shifting, and we can have the model tell us how a load shifting control strategy would have performed that very day. And so that might look something like this, where here we have that same plot, only I've added orange data, which is an example of what simulated data might show for the load shifting case. And you can see for the hot water consumption and electricity consumption in the morning, there's no change. Load shifting doesn't start doing anything until 10 a.m. And so we won't see any changes in the performance of the water heater before 10 a.m. But then at 10 a.m., you can see that the water heater in the load shifting case starts consuming a little bit of electricity. And this is the heat pump gradually heating the water from 120 to 135. And then at 3, it reaches 135. It's at the set temperature. It stops heating. So now we're going back to this. Well, now we have a situation where neither the base case nor the load shifting case are consuming any electricity at all. And then we get to the evening draws, those 2 showers after people go for runs and the dishwasher use. And you can see it might be a little small, so maybe you need to squint a bit, but you can see that in the base case, the water heater starts consuming electricity earlier. And this is because, as people take energy out of the tank, you need to add electricity sooner without the load shifting just because there was less energy stored in the tank. So it starts using the heat pump earlier. And then later, there is a fair amount of hot water use here. So later, the load shifting case still engages the heat pump, but that comes in about an hour and a half later in this example. And as a matter of fact, in the load shifting case, it starts using the heat pump right around the same time that the base case started using the resistance elements. And the load shifting case never has to use the resistance elements. So this is an example where load shifting didn't have as much impact as we wanted. We wanted no electricity consumption during the peak period. But since we didn't have to use the resistance elements, it had a big impact. Not perfect, but big. And so this next slide just kind of adds arrows, which shows you the impact that we're able to see on that particular day because of simulating the load shifting case using the monitoring data. We can really directly compare the base case, what happened on that day, to the load shifting case and what would have happened on that day. So here comes what I think will be the very interesting part. I'd like to open it up for discussion. I'd like to hear your thoughts. Do you think this will work? Do you have recommendations for ways we could improve this process, or are there potential other applications? I've talked about water heating. Maybe it's going to be very useful in some other situations. So I'd like to hear what you have to say. And here's my contact information.
Peter, great. Thank you for that presentation on water heating specifically and using simulation models to help do the analysis. I think it's, a lot of what you said really resonated with me, in particular, the idea that statistical methods have a hard time addressing the fact that the periodicity, so to speak. I run my washer at different times during the week, but maybe on average every week I run it 3 times. But the statistical methods have a hard time knowing that. And so I think the simulation models show a lot of promise in capturing that specific variability. And with your issue of focusing it down on hot water, of course, it's a little easier to do that analysis and focus on one piece of equipment. So I guess one of the questions that's coming up, and oh, by the way, we have a really full room out there. I hope you have plenty of standing room and socially distancing wherever you are, but we have over 167 people attending today. So thank you for all of you that are attending. And please, if you have questions, fire them off. We do have 9 minutes and 52 seconds for Peter to add more intelligence and wisdom to this session. So with that though, the simulation model, which is the basis of your analysis, how accurate does it have to be, both at like the whole building level or just the piece of equipment? What's the trade-offs in terms of building a model that's good enough using simulation tools?
Yeah, I think that's a really important question. And I kind of heard 2 questions in there, so I'll try to address them both. You asked about how accurate the model has to be at the equipment level and at the building level. And I think, well, fundamentally, the model has to be extremely accurate in order for this to work, I think. We're trying to say, here's what it would have done on a day without, or I'm sorry, we're trying to say, here's what it would have done, on the day with the controls that we didn't have or with the equipment that we didn't have. And so our ability to answer that question is only as accurate as the simulation model we're using to answer that question, which really means it has to be pretty darn accurate. Fortunately, I think this is a challenge that we can overcome. I know a lot of the simulation models are tested against experimental data. They're not considered valid unless they go through rigorous testing and have errors less than the measurement uncertainty. So we're talking about a couple of percent. I'd also really like to highlight, at least in the water heating world, a company up in Seattle called Ecotope has a model called Heat Pump Water Heater Sim, where they've done testing on several different water heaters, several different heat pump water heaters, and pulled out the specific parameters needed to model specific pieces of equipment that people can buy. And I think this is exactly the kind of approach that we need if we're going to start using model enhanced monitoring, because then you don't have a simulation model of a heat pump water heater. You have a simulation model of this heat pump water heater, which I think makes all the difference. Then you also asked about building level, and if we're trying to expand this out from a specific piece of equipment to the building level, I think that can get quite challenging, because then we need every single model of every single piece of equipment in the building to be accurate, which, we could probably do that. There are definitely challenges, but we could probably do that. But I also think at that point, getting all of the monitor data necessary for, emulating the occupant behavior might get a little harder. Do we have data on when the occupants opened the windows versus when they didn't, for instance? That could be a real challenge if we're trying to do this for an HVAC-based technology. So I think, it might make a lot of sense to really focus at the piece of equipment level, at least for now.
That's fascinating. What I'm hearing is absolutely everyone should be out there learning how to use the most sophisticated and best tools they can and looking for options like Ecotope, and maybe starting with specific technology is a good place to start. The promise is, of course, one day we'll be able to do whole buildings. I think all the other speakers have talked about this as well. I know I'm really thrilled about that as a direction for the industry. I'm really happy to see M&V, the first 3 speakers promoting simulation models as part of their M&V. So that's great. From the audience then, with the 120 degree F to 130 degree F Fahrenheit domestic hot water heating strategy, what considerations do you need to make it safe? Legionella is one concern. What are your safety concerns given everything that's going on in the world?
Yeah, that's always a good question that comes up. Legionella is definitely a hot topic in the water heating world. I unfortunately do have to preface this by saying that it's not my area of expertise. I'm not exactly an expert on Legionella. Um, so maybe if you send me an email, I'll try to point you to the best resources that I know about it to look up the precise numbers. But general rule of thumb is that Legionella does not grow above 120 degrees. So if your water heater is at 120 degrees, it actually can cause a little danger with Legionella because there's stratification in the tank. If it's set at 120, that means the top is 120 and the bottom is probably colder. So you do sometimes, it's very rare, but you do sometimes see Legionella grow in those environments. Fortunately, one of the benefits of load shifting is that as you get above 120, just the fact that the water is hot starts killing the Legionella, and the hotter you go, the faster the Legionella dies. So when you're doing the load shifting and bringing the water up to 135, especially with a heat pump water heater, which injects the heat at the bottom of the tank, so it even gets the colder reservoir down at the bottom, you're basically increasing the whole tank up to 135, which will gradually kill Legionella. So load shifting actually makes it safer in this regard.
Thanks for that. And again, I'll reiterate, you said you'd offer for clarifications on that if people want to reach out to you later. So
Hmm.
let's
Absolutely.
think with that. Great. So in this project, this monitoring project where you had multiple sites, and this gets a little bit to the what other characteristics of these 10 sites that were unique or not so unique? How common is the installation, and how customizable does it have to be per site?
Yeah, so this site is an affordable housing project in Davis, California. Angel, I'll just kind of give you a little hint that within Frontier, you might have people you can talk to get some good details on this project. Um, and there are actually a couple things that are very unique about this project. First off, load shifting is still a topic that's being researched, so that's one of the non-traditional characteristics. Second, it's using a process called clustered heat pump water heaters instead of either individual or central. And so what I mean there is in a multifamily building, a big apartment building or a condo building, you'll often see either each dwelling having its own water heater, that's what we call individual water heaters, or you'll see a big central plant with a lot of water heaters, a lot of storage tanks, and a big recirculation loop taking hot water around the building, and that's what we call central. In this case, people have kind of realized that a single heat pump water heater can serve more than a single apartment. So in this case, they have one heat pump water heater that's designed for a single family house, serving 4 apartments. Part of the reason they're doing this is that these apartments are typically 1 bedroom, sometimes studios, so they're expecting 1 occupant. A few of them are 2 bedrooms, so maybe 2 to 3 occupants. But this kind of says that, any given heat pump water heater serving 4 dwellings will really be serving somewhere between, say, 4 and 8 people, which the industry generally believes will be successful.
Great, thanks. Back to M&V and load shifting, and we also have now demand response. And I'm wondering how that complicates M&V. That's sort of a general topic. But and the question here is, I think the struggle in most real world conditions to load shifting in a commercial setting. So how does this work in a commercial setting where the loads are fairly reliant on people being present to work at specific times? So what solutions do you see in commercial load shifting?
Yeah, that's a really good question. And I would say, in the question, you kind of captured the real essence there when you're talking about it. The load is all dependent on people being there to do the work. And so I think a lot of the answer to the question lies in the type of building that we're looking at. If it's, say, an office environment where people are typically leaving before 6, then there's probably not that much need for load shifting because you're really trying to shift load from that like 4 p.m. to 9 p.m. window over to earlier in the day. And in the office environment, you only have people occupying the building in that 4 p.m. to 6 p.m. part of the window. So yeah, you could probably get some benefit by increasing the set temperature earlier, but not as much as in the residential case when people suddenly get home and start using electricity. Then there's another example, I think, of commercial kitchens. And I'm pursuing a project studying that, where commercial kitchens have the really big hot water load washing dishes around lunchtime, and then they've got a bit of downtime before dinner time when they're going to suddenly have another really big hot water load washing dishes after people use them for dinner. So that, I think, is an area where there's possibility for load shifting for sure. I could see gymnasiums, a lot of hot water for showers after people work out at the gym. There's possibility for load shifting there.
Great. Yeah, I think it depends. It's the engineering answer. You really got to look at the loads and the makeup of the equipment and all that together. All right, so you've said you've got a project underway where you're trying this overall process for the first time. When will you be able to report the results and how well it's working?
Yeah, we've recently started monitoring at the building, and unfortunately, the project's been delayed by COVID because we need people to move into the building before we can really collect data. So it's being slowed down. We expect to have the data we need to really truly do the project about this time next year. That would give us a year of monitoring data. And then one lesson we've already learned is that when you're designing the monitoring plan and choosing your sensors and where to put them, you really have to choose them with providing the information the model needs in mind. So one example is we've got BTU meters looking at the cold water entering the building, the hot water going to the building, and yes, there's a mixing valve so that the mixing valve is set at 120 so that even if you have 135 coming out of the water heater, the maximum temperature going to the occupants is 120. And so we've got the temperature entering the building on the cold side, going from the mixing valve to the building, and the flow rate going from the mixing valve to the building, which really means we don't have enough data to know exactly what's coming out of the water heater, either the flow rate or the temperature. And so that's one lesson we've learned. You really need to make sure you get the measurements on the flow rate through the water heater in order to do this really well.
That's great, Peter. Thanks. So hire a professional if you want to do one of these projects for the metering lessons and all the
For now,
experience they've learned
hopefully
in
we
the
get it
field.
streamlined.
Right? Maybe it'll be a general protocol. Thank you very much, Peter. Concludes our third speaker. To keep it on time, here we are, the final speaker today in this absolutely fantastic session. And his name is Mr. Timothy Burrows. I have the pleasure of working with Tim on a couple of projects. Tim Burrows is a president and CEO of Sustainable Returns Incorporated. He is a specialist in energy efficiency, renewable energy, and measurement and verification. He's a strategic, data-driven thinker, and over a 25-year career, he has consistently used these characteristics to partner with like-minded clients. Thankfully, there are some that like data, and to achieve environmental outcomes while simultaneously boosting their bottom line. So looking for the financial aspects. Tim has 25 years international engineering and project management experience. He holds a Master of Business Administration, major in technology management, and a bachelor degree in mechanical engineering. Welcome, Tim.
Okay, everyone. Well, welcome to the show. My name is Tim Burrows, and today we're going to be talking about managing risks in ESP contracts. So before we start talking about that, just a quick intro. First of all, Sustainable Returns is a consulting business. We work in the industrial and commercial sectors. We are product agnostic. That means we don't care about what brand we're using. We just try and find the best equipment for the job. We specialize in energy savings performance contracts, measurement verification, and we also conduct energy efficiency studies, predominantly with Bonneville Power Administration through their Energy Smart Industrial program, but also with other companies. We conduct cogeneration feasibility studies, renewable energy studies, and we also provide project management. I think you get a bit of a background on me, so I won't go through that in a lot of detail. Based in Kirkland and originally from Melbourne in Australia. So let's talk about risk though. First of all, pretty straightforward. I think most people would understand it. It's an uncertain future event. It's not something that has happened, it's something that might happen in the future. And it carries an impact, a measurable outcome. And importantly, that outcome may be positive or it may be negative. So a lot of people talk about risk and they think automatically, oh, something that's bad is going to happen, we have to avoid it. And that's true. But there's also the potential for positive events. And if possible, we try to enhance those events as well. But we're probably going to focus mostly on the negative events at the moment, because those tend to be something that's more common in projects. Okay, so risk management is essential. The aim overall is to improve the likelihood of achieving your objectives, an essential part of project and organizational management. And if you ignore it, it can lead to major problems. You know, I've plenty of experience with projects where issues occurred that could have been foreseen, and if they had been foreseen and planned for, they wouldn't have occurred. Everything from the space shuttle disaster down to arguments over how savings should be calculated in a performance contract, and we'll talk about some of those more specifically shortly. There are international standards. There are industry frameworks, there are organizational frameworks, there are many alternative ways of managing risk. The Project Management Institute has a framework which is incorporated into its project management body of knowledge. Project managers out there, be familiar with that. The International Standards Organization has ISO 31000, so management framework, and you will find national and government standards. But what they all have in common is a general approach, which is to identify risks, qualify them, plan responses, and then monitor it as the project progresses. All projects carry risk for sure, and some projects are riskier than others. ESPCs are very interesting in that they are riskier than a typical lump sum contract. Not only do you have the standard risks that could occur in terms of, you know, equipment not operating as it should operate, or you know, delays, or you know, unexpected price increases, things like this. But on the financial side, you also have to deal with, you know, potentially changes to payments that in a lump sum contract could be relied on. So that ESPs are riskier. Well, first of all, we can't measure savings. For those of you who have completed the Certified Measurement Verification professional course, this will be well understood. But savings are estimated, not measured. And anytime you estimate something, there's room for arguments. It's difficult to accurately calculate the uncertainty in estimates. And this might sound trite, but when someone shows up with an invoice that says, here is the amount of energy that we saved, and this is the financial amount that goes along with that, and now I want some money for this, there's opportunity for the other party to say, well, how do you know that's the correct amount? Now, there's been a lot of effort dedicated to trying to articulate the uncertainty that goes along with savings calculations, and there can be confidence intervals that can be placed around. There's all sorts of statistical judgment, but at the end of the day, there's still a lot of opportunity for arguments when it comes to this, to estimating savings and seeking for those savings estimates. So this risk has to be managed, and there are ways of doing that. Non-routine adjustments to the baseline can have a very large impact on savings estimates if they're not detected. So operational hours, other types of changes that could occur if they're not measured in a routine adjustment, and if they're not detected, someone changes the usage of a space, or they change the operational hours without telling anyone and it's not detected, the actual energy consumption is higher than expected, people wondering what's going on, that can affect the payments. So these non-routine adjustments are a very important part of measurement and verification, and they're often overlooked. And the baseline might not exist, or there may be partial information available, and we'll talk about that in some upcoming slides. It's also difficult to accurately calculate the uncertainty of models, building sim models, which are used to set the baseline, particularly if you're using option D in the IPMVP. The simulation models are subject to error, but that error is difficult to estimate. And logging equipment often fails. You'll have large portions of zeros or no data, and that requires interpolation, questions around how that interpolation was calculated, that can lead to arguments. So all these risks apply to ESPCs, not so much to a more typical contract. And that means we need to be a little more careful when we're involved with an ESPC. Okay, so management generally. As I said at the start, it's really a sequential process. We start off, we identify as many risks as we can think of. We qualify those risks. We prioritize them to focus on the important risks. We come up with responses to those important risks. And then as the project progresses, we monitor those risks. And during the monitoring stage, we identify new risks. Some of the old risks get removed, some of the new risks included, and we check to see the status of each one. So let's run through some of these steps. So first of all, when we're identifying risks, categories can sometimes help. So anything that's in a past project, that's gone wrong in a past project, is a rich source of information for the identification process. But if we look at categories, these can also trigger ideas. So regulatory category might include things like changes to incentives that might come from a utility, or changes to power prices that might affect savings calculations. There are counterpart risks. Pretty easy to imagine what types of things might go wrong between the client and a supplier, or the supplier and a subcontractor. The availability of data we talked about, financial risks, operational risks, performance risks. So we'll talk about those next slide. So these risks around financial operations are very typical to ESPCs. The DOE has thought about this a lot, and if we look at the different categories here, they've identified several different kinds of risks that fall into each one of these categories. So we can look at interest rates. Interest rates could change. If they change, that's going to cause an impact. Construction costs. These are typical risks of all construction type projects. M&V confidence is an important one. So the existence of a good measurement and verification plan, which is a part of the ESPC, is very important to having a smooth experience. A well-written M&V plan will cause a relatively painless experience. A poorly written M&V plan can lead to lots of arguments and disputes. Energy cost savings. How are those energy cost savings going to be calculated? If energy cost savings are not calculated correctly, or if there's a dispute over how they're calculated, that's going to lead to problems. There could be project delays, changes in the use of a facility. We'll talk about those in a moment. Operating hours. If there's changes in operating hours, how do we account for that? Are they part of the routine? Are they measured and part of the routines, or are they actually something that's stipulated, or is it going to be something that is actually calculated after the fact? Operating hours are one of the really difficult areas, because it's difficult to measure in many cases. And so having a clear agreement on how that's going to be calculated and monitored is very important to have up front. The load profile is important. The weather is something that a lot of people don't necessarily look at carefully enough. So the correlation between energy consumption and weather is a sort of a, it's an assumed thing. But if the baseline information hasn't been carefully evaluated to determine that there's a good correlation, then a poor correlation might lead to an inaccurate baseline adjustment. To what extent are optional people available and motivated to participate in the process? These can lead to problems down the track. The performance of equipment, obviously. operations, maintenance, and equipment repair. You know, if equipment isn't properly operated and maintained, that can cause problems down the track as well. So these are all risks that can potentially get in the way of success. Okay, so we have a long list of risks, and the question is, what do we do with that big long list? So this qualification process helps to establish the important risks and separate those from the ones that don't need as much attention. You see in the top left here, we have what would be called a risk register. So we have a list of the risks down the page, looking at the probability and the impact of each one. And then based on that probability and impact, we have a score, and we simply rank them from the most extreme risks down to the lowest risk. Underneath this, we have our risk scoring matrix, and that basically helps us to score each risk. So you can see, for example, that a rare probability risk that has an insignificant impact will receive a low score, whereas a catastrophic risk that is almost certain will get a very extreme score. One thing that's worth pointing out here is that catastrophic risks, these include fatalities, or the project being abandoned, very major outcome. Even if it's rare probability, they're still classed as a high risk, because something that could cause that much damage or that much of an issue needs to be managed. So the flip side of that is something that has an insignificant impact but is almost certain to happen. We might still call that medium. Now, people can play around with this scoring matrix. They don't necessarily have to do it exactly as it's shown, but that's looking at it. Okay, so once we've figured out which risks are the most important ones to look at, then we decide how we're going to respond to those risks. So there's 4 generic responses, and this is a sort of a hierarchy that we can look at. So for the most important risks, you're going to start off and you're going to say, well, first of all, can we avoid it completely? You know, can we do something to make sure that it's just actually not possible for that to happen? Change the design. You know, can we look at ways that will just fundamentally make it impossible to occur? The next option that we could look at is to transfer that risk, which means moving the impact of that risk to another party that's in a better position to manage it, to deal with it. And that's a typical example of that would be to take out insurance, where you say, well, okay, we're just going to pay this part over here to take the exposure on that risk, and they're in a better position to deal with that than we are. Or it might be that you say, well, if we fix the interest rate, that might transfer the risk over to the bank, because if interest rates change, they take on that risk. Mitigation is the most popular one. It's the first one that most people think about. How do we reduce the probability of impact? How do we try harder to make sure this doesn't happen? Or how do we design something that makes it less likely to occur? We still think it might occur, but it makes it less likely. And then the lowest response, which often applies to risks that are sort of insignificant, not that important, is to just simply accept that risk. And that means to deliberately take no action. So it doesn't mean that we say, well, let's forget about it, not think about it anymore. It means that we say, well, what's this risk and how would we deal with it if it occurred? Perhaps we have some money in our financial contingency reserve. Perhaps we have other organizations in place that say that if and when this occurs, it will be taken care of in this way. Okay, so that's the generic approach, where we look at the identification, qualification, the putting together our responses to the risks, and then once we've done that, then we look at monitoring. But I wanted to take you through a couple of case studies where some issues occurred and think about how that relates to risks, and specifically to some risks that occur in M&V projects. So the first case study, I've got 2. The first one is occurred at a higher education sector, a very large greenfield project with multiple new buildings being constructed over a period of several years. The size of this was around 1 million square feet, 1 million GSF, and there were probably between 10 and 15 reasonably large buildings being constructed. So right at the front, the owner identified the risk of potentially inefficient design, which would lead to high life cycle costs. So they didn't want a cheap building that would then consume a lot of energy. They wanted the contractor to come in with a good design of building that would have an efficient energy profile, leading to an optimal life cycle cost. So how do we go about that? Well, the chosen response was to set what was known as a pain share, gain share arrangement. What that involved was setting a target consumption for each building. And if the consumption was lower than the target, then both parties shared the savings. And if the consumption was higher than the target, then each party contributed to the overrun. So it wasn't all on the owner, but it wasn't on the developer entirely. So that sounds pretty good. One thing that was not ideal was that the decision was that the target would be set using an uncalibrated building energy simulation model. So rather than setting it up front, which would be very difficult, or setting it after, which would potentially lead to embedded inefficiencies, the idea was that the developer would build a model using eQuest in this case, and that model to predict the consumption of the building, and then that consumption would be used as the target. That prediction would be used as the target in practice. This was not ideal. It led to a very, very complex situation. The contract asked for LEED Platinum certification. It had to comply with California Title 24, savings by design. There was a contract compliance target in there, which involved an energy model. And there was also an energy target that we just talked about. So there were 5 set energy models that were required to be produced, and they were produced by 2 different contractors. But primarily, there was a lack of confidence that the energy model would be accurate enough to produce a target that was useful, particularly given that it was uncalibrated. And what this led to was that the owner wouldn't accept the target ultimately when it was provided, even though that was what was written into the contract. Further to this, the contractor would not provide the model for review to take place. And so it led to a stalemate between the parties where neither party could agree on the target. The party that was providing the target didn't want to be transparent about how the task related. The party that was accepting the target wasn't comfortable that the target was reasonable. And so they couldn't agree. And actually, the targets were removed from the contract, at least at the time of. So what can we take away from this? Well, really the underlying issue was a poorly thought out M&V approach, which, if you go back to our earlier slides around contract risks, falls into the confidence category. There was not enough confidence in the M&V approach for both parties to be comfortable when finally the time came to evaluate the calculation of energy efficiency. This was exacerbated because there was internal review from stakeholders pre-contract. The contract team that was drafting the actual contract documents decided that it seems that they decided they weren't going to heed those comments. And by the time the expert team was engaged, the contract had been signed and the project was in progress, so it was very difficult to alter. So, what can we take away from this? Really, the important thing here is to obtain advice from, qualified and experienced M&V professionals before the tender documents are released. Because if an M&V professional had looked at those documents, the first thing they would have said is, this is potentially problematic and we need to look at a different approach here. So the second case study is for a national, what we call, I guess, a super ESCO in Western Asia. And this government organization is implementing a program to introduce the ESCO model to their country. The idea being to encourage local companies so that they can build capacity delivery of projects using ESCOs and ESPCs. So one of the challenges, of course, in any kind of government type of project is that it's going to be constrained by the bureaucracy. And the organisation identified that there would be a risk of inaccurate or incorrect savings predictions from suppliers, and they didn't want to invest in suboptimal projects that were based on savings predictions that would never come to pass. So, a reasonable consideration. They didn't want to be overpaying for projects. So they did the right thing, based their operating guidelines on widely accepted IPMVP standard, and projects were evaluated using the IPMVP principles. So this includes how to calculate the baseline, savings calculations, and evaluating uncertainty. In this case, some of the issues that were encountered, primarily the department's success was being very much based on the rate at which projects would be put through the pipeline. There was a lot of pressure to keep pushing projects through. They wanted to see growth, understandably. And so they wanted to achieve their targets. And so this led to a desire to sort of push forward with projects and get these projects underway. But often this would occur before the M&V planning was complete, and this led to insufficient or non-existent baseline data, which again, we talk about that in some of those risk categories earlier on. It was something that was foreseeable. And what this caused was some tension between the documented approach of let's do A, then B, and then C, and sort of more creative methods to calculate savings using information that wasn't quite complete. The problem was this caused another stalemate, and this is what we find in M&V projects or projects for energy savings performance contracts, where we have two parties who have all good intentions, who want to go ahead, they want to get the project implemented, but there's this problem that appears between the approach that has been proposed for measurement verification and then the reality of what occurs when you get to the point where people are ready to start exchanging, money. Often that leads in a stalemate, arguments, difficult to resolve these arguments, and then things start getting thrown out. So what can we learn from this? It's a difficult one because it's very, very common for projects to be pushed forward in the absence of the information that's really needed to put some good quality M&V planning and documentation in place, specifically baselines. The baseline period is very important, and particularly for buildings where you need a good maybe 12 months even of baseline data to make sure that you've got the range of variables to properly adjust in the future. What can we say? We can say that we need to plan the M&V early. But in this case, I think there needs to be flexibility in the guidelines so that parties can agree on alternatives if necessary. For example, in many cases, in this particular case, in this particular study, this case study here, there were projects where very little data was available, but some data was available. It may have only covered 3 or 4 months out of the year. And the question is, are you comfortable with the risk? We can use this data. It's not necessarily valid outside of the temperature ranges that we have, but it can be used. There's a risk associated with it. Are you willing to take that risk? And if the answer is yes, then both parties agree, move forward. But if that's not the case, and often that's not the case because one party might be risk averse, then more rituals and processes need to be put in place to ensure that the baseline data is collected early and everyone understands that we need this much data. It needs to be collected over this period of time. And it needs to cover a certain range. So different approaches depending on the needs of the project. And this is something that is common across all ESPs, all M&V. It's not that the calculations need to be accurate to 90%. They just need to be agreeable to both parties. Okay, so that's probably, hopefully that's given you a bit of an overview of the types of risks that occur or can occur in ESPCs and a way of dealing with them. Some examples of the types of risks that certainly are. But the summary here is that ESPCs are riskier than typical contracts, and so we need to take extra care. And risk management is critical. So we have to identify, we have to qualify, prioritize, respond, and monitor. And in doing so, draw on previous experience, draw on the experience of those that are professionals that work in this area and have been through this before. That's usually your best bet. Thank you very much. And I will be available for some questions.
Great, thank you, Tim. Keeping on Angel's theme of the labyrinth, it feels like you've walked us through the M&V labyrinth with a different view, looking at different, focusing on different part of the whole problem. And I've always loved that structure of looking at risk specifically as an M&V issue, and you know it's taught in the class. So with that in mind, though, on that first project you were discussing, you said, you know, maybe the M&V person should have gotten involved earlier in the process. What might you have recommended if they'd gotten involved earlier? What do you think would have come of that project, which, by the way, sounded vaguely familiar to me?
Well, I mean, the project itself was very large and very complex, and but the key issue that the parties were experiencing was this discomfort, this disagreement around the way that the energy target was set in the first place. And if you really trace that to the root, it was concern around the accuracy of the number that came out of the model, and furthermore, that was really ultimately because the model was uncalibrated. So, and we advised them to do this, but it was a little bit late. Unfortunately, as I said, the contract was already signed. It was a big, expensive contract, very difficult to get modifications to it. But had they have, I think, approached us prior to contract signing and talked about it, that would have almost certainly recommended that they had done a calibrated approach. So, to build the model, build the simulation model, commission the building, and then spend some time calibrating the model to the building so that you had more accuracy and more confidence in the actual ability of the model to provide an accurate and an agreeable figure.
Great, thanks, Tim. So I'm hearing a theme. We're going to close now. In the next minute, I'll have another question. I apologize for those of you that sent in questions, but we're up a little bit over time already. Give Tim one more, and that is, a couple of people are asking about risks in terms of just the data itself and potentially failing. So we know that we might have gaps in the data, whether it's weather data or the data loggers themselves. So what can you do to manage that? What's an effective way to specify something that might prevent data loss or backup so you don't have to fill it in?
Yeah, and there's really two approaches to that. I suppose the first one is a sort of the mechanical approach, I guess, which is how do you stop it occurring in the first place? How do you reduce the likelihood that will happen? And the specific issue that we saw at this project was that the data they had set up was sorry, batteries running. The data logger that was set up was connected to mains power. So when the mains power went out, the logger went offline. And so they did actually go ahead and connect that to an emergency uninterruptible power supply so that it would continue to log even if there was some sort of interruption in mains power. But the other side of it is to think about in advance, is to say, well, we probably can't rule that out. In other words, there's probably no way of assuring that will never happen. And so the question becomes, well, let's think about this and say, what happens when this occurs? How do we deal with it? Can we agree on the approach that will be taken to interpolate the data so that we all agree up front how to treat that? And it might be as simple as saying, take the most recent period from the same time of day and just drop that in and scale it. or there might be more complex ways of dealing with it. But whatever you come up with, both parties have to say, yes, we agree with that. And if you do it up front, before the stakes are too high, then you're more likely to get agreement rather than waiting until after the fact and then trying to reverse engineer something down the track.
Failing to plan is planning to fail. Thanks, Tim. That completes our session. Again, thanks, Tim, for your final panel, fourth panelist there. Thanks to all of you for sticking around. Here we had 150 people left at least still. Hope you enjoyed this this first inaugural virtual conference for AEE West. Hope you enjoyed the day. Now we're going to hear from AEE's Executive Director, Bill Kent, for some closing comments on today's sessions. Take care, everybody.
Wow, what a great first day. I'd like to thank everyone for attending and participating today, day one of the AEE West Virtual Energy Conference and Expo. We started out with a fantastic opening this morning from Dr. Martin Keller, good networking, visiting with our exhibitors in the virtual expo, and an informative conference sessions this afternoon. So looking ahead, we want to preview day two. We kick off tomorrow morning with a keynote plenary with one of our co-hosts, Seattle City Light. We're honored and fortunate to have Deborah Smith, General Manager and CEO of Seattle City Light, opening our program tomorrow at 9:30 a.m. I'd like to also say we'll have a live question and answer session with Ms. Smith immediately following her remarks. Following that, we'll have at 10:30 to 11 our second day, round two of our Innovative Technology Showcase, rapid fire preview of the latest technologies and solutions from our exhibitors with our virtual expo hall, 10:30 until 12:30 p.m. The AE membership and certification booth will be open, attending networking in the virtual expo. Have a short break for lunch, and in the afternoon, two concurrent conference sessions. First one, incentives, financing, and utility programs. The second concurrent session, building success stories. So we certainly invite you to join us for day two, and thanks for your attendance, and we will see you tomorrow.